All right, our next section is 2.3. Yeah, so section 2.2 had all of these what they call basic derivative rules, and especially like the sum and difference one and the constant multiplier one, they act like you would hope and expect they would act, right? I mean, they do what we sort of would expect them to do. And I mentioned last time when we first started that section that the same thing would not be true when we got to products. And that's what this section is products and quotients, and they don't work the way we would expect them to work. But I want to show you, in fact, that they don't. So we're going to do an example of one, and the question is the product rule. Is it possible, like with the sum and difference rule, that when we take the derivative of a product, it's just the product of the derivatives? We can just take the derivative of each piece, multiply them together, and be done, because that's kind of what we would hope for. It works for limits. Limits work that way. So does it work for derivatives? That's the question. So what we're going to do is we're going to consider two functions. The functions we're going to look at are f of x equals 4x to the 9th and g of x equals x cubed. And I've purposely chosen very simple, clean ones to work with so that we can examine this property. The first one here says what we're going to do is we're going to multiply them together and then take the derivative. So I have 4x to the 9th times x cubed. So again, I want to take the derivative of this after I multiply. So we're going to multiply first to work inside the parentheses. So what is 4x to the 9th times x cubed? 4x to the 12th. Right? Property of exponents says I add my exponents. 9 plus 3 because they're exponents. And then we're going to take the derivative. Okay, so the 4 stays, and then the 12 will come down, right, and be multiplied by the 4, which will give me 48. And I'll decrease my exponent by 1, which will give me 11. 4x to the 11. And that actually really is the derivative of these two things multiplied. That's the correct answer. But the question is, could I have multiplied each of the individual derivatives and gotten the same thing? So we're going to look at that next. So on the next piece, what we're going to do is we're going to take each of the original functions and take their derivative. So this was 4x to the 9th, and we're going to take its derivative. And then this is x cubed, and we're going to take its derivative. So 4x to the 9th, my 9 will come down multiplied by my 4, which gives me a 36. X to what power? The 8th. On the other one, x cubed, what's the derivative of x cubed? 3x squared. Yes. Now I'm going to add or multiply these two together. So I've got 36x to the 8th times 3x squared. What is 36 times 3? 108. And my exponent on my x's would be what? A 10. And what I want you to see is that the results aren't the same. I cannot just take the derivative of each part individually and have the same result. It doesn't work. So this is not true. This is a no. So what is true? Well, this is actually the product rule. When I want the derivative of a product that I can't clean up first, because see, the last one I could clean it up first and take the derivative, right? I could do that. Totally cool, no problem. Sometimes you can't do that. So the derivative, and I will openly admit that I write mine backwards from what your book writes it. It doesn't matter. It ends up being the same thing because addition is commutative. But it's the first function, as is, f of x, times the derivative of the second function, plus the second function, as is, g of x, times the derivative of the first function, f prime. And just for fun, so that you can see that I'm not trying to, like, trick you, I want to use that same example that I just did and show you it would have worked if I did it this way. So on the previous slide, I had that my first function was 4x to the 9th, and g of x, the second function, was x cubed. We found that our first derivative, or our derivative of our first function, was 36x to the 8th. And the derivative of the second function was 3x squared, right? Those were all details from the previous slide. I'm just rewriting them. This is saying I should take the first function as is, so that's 4x to the 9th, multiply it by the derivative of the second function, which was 3x squared. And then I take the derivative of the first function, which was 36x to the 8th, and I multiply it by the original second function, which was x cubed. Okay? What I'm really trying to do is convince you. This is not a proof, but it is an argument with a specific example so that you can see it would work. 4 times 3 is 12. X to the 9th times x squared is x to the 11th. 36 times my 1, if the other one is 36. X to the 8th and x cubed is x to the 11th. And what is 12 plus 36? 48, x to the 11th, which is exactly what it was when I multiplied them together first and took the derivative second. So this, although it doesn't feel intuitive, it isn't what we wished and hoped for, is in fact the product rule. It's what works. So we're going to use this product rule and take some derivatives, okay? You will not be asked to do anything that I just showed you to verify that it works. That's not my point. My point is to simply show you that it really does work. So we're going to use it now. So we have a function given to us. And this is actually one that if I really wanted to, I mean, like we could multiply this out, right? We could multiply this out and we could take the derivative and clean it up. It would be all good to go because they're pretty simple functions being multiplied, like the first example I did. But we're trying to do this using the product rule for practice with something simple. So the product rule says that I take the first function and I rewrite it. And then I take the second function's derivative. So what's the derivative of x squared? 2x. And the derivative of the negative 5? 0. So we're done. And then I've got the second half of the product rule. I add. Now I want the derivative of the beginning part. What's the derivative of x squared? 2x. And the derivative of the plus 3? 0. And I multiply that by the original of the second one, which is x squared minus 5. Okay, and then we clean up as much as is possible for the problems we work with. On this one, we can clean it up quite a bit. So we're going to distribute. X squared times 2x would be 2x cubed. 3 times 2x would be 6x. We'll do the same thing over here. 2x times x squared would be 4x cubed. 2x times 5 is negative 10x. And if I combine like terms, what do I have?
4x squared is supposed to be 2.
Oh, which one's messed up? Oh, you're right. This one was supposed to be a 2. Thank you. Everything else okay? Okay. Then, if I clean up, what do I have? 4x to the third minus 4x. Everybody good? You know you always start out easy, right? The problems start out pretty clean and simple, and then they get harder. So let's see that happen. The next one's got some trig in it, which makes it a little interesting. All right, so on this one, two pieces again, right? The first piece, I simply write down x cubed. What is the derivative of cosine of x? Negative sine x. Please remember, like I told you last time, either put the negative in front of the x cubed or put parentheses around the negative sine x. Don't make it look like subtraction, okay? Adding, what's the derivative of x cubed? 3x squared. And then it's rewritten times the cosine of x that we began with. Truly not a lot we can do to simplify, so in some regards this one's nicer than the last one. It's negative x cubed sine x plus 3x squared cosine x. Okay, that's product rule. I'd like to show you quotient rule. And we're going to verify again the same kind of thing that we did on the last one. We would really, really love it if the quotient rule said that the derivative of the quotient is the quotient of the derivatives. So again, we're going to use those same functions that we had before, and we're going to check and see what happens. So I have 4x to the 9th in the numerator and x cubed in the denominator. And then I'm going to take my derivative when I'm done. So what is the simplification of 4x to the 9th over x cubed? How would that simplify? 4x to the 6th. And what's the derivative of 4x to the 6th? 24x to the 5th. Everybody good with it? So that is really the answer to this particular problem because I was able to simplify before I started. Please simplify before you start things. Don't go using quotient rules if you don't need to. We're about to learn how complicated they can be and messy. So let's see what it would look like if I had taken the derivatives separately and then divided. So I have 4x to the 9th, and I'm going to take its derivative. And I have x cubed, and I'm going to take its derivative. So what's the derivative of 4x to the 9th? We did this a minute ago. 36x to the 8th. And then the derivative of x cubed was 3x squared. If I simplify, what do I get? 12x to the 6th. And the reality is those don't match, right? So this is a no. Again, does not work. So what will work? Well, this is the quotient rule. And everybody shake your head really hard if you're like, yeah, I don't want to do that if I don't have to. We do not want to do that if we do not have to, right? There's a lot going on in this particular rule. You'll notice that the numerator looks an awful lot like the product rule, doesn't it? It's reversed. That is, the image of how I wrote it is reversed. And there is a subtraction sign in the middle instead of an addition sign. And the denominator has the denominator squared in it, the original denominator squared. So what I'd like to do first is, again, show you that it really will give me the result that the other one wouldn't. So again, I had f of x is 4x to the 9th. G of x is x cubed. F prime is 36x to the 8th. And G prime is 3x squared. So if I really tried this rule with those pieces, I'd have an x cubed here. The derivative of the first one, which is 36x to the 8th, minus 4x to the 9th times 3x squared, divided by the original denominator, x cubed squared. Now we're going to have to clean up a lot to see that it works, so that's the next step. I do in fact have 36 here, x to the 11th, minus 12, x to the 11th, divided by x to the 6th. So what is 36x to the 11th minus 12x to the 11th? That would be 24x to the 11th. And what happens when I have x to the 11th over x to the 6th? You subtract and you get 24x to the 5th, which is exactly what I was supposed to be getting. So it does in fact work. It's just messy. So we should do one, right? Did everybody get it written down okay? All right. So you can take a look at number 3 here and you can see pretty quickly why you can't always simplify first. The example I did to begin with had a monomial, one term, over another monomial. And so I could clean up and simplify before I ever took derivatives. I can't do this because there's a binomial on top and a binomial on bottom. So there's no way to simplify this to start. But I still can use the quotient rule that we developed, or that we found. So to do this, again, T is another letter that's super not friendly to do. Make sure if you're using your T's, they don't look like your plus signs. I put curls on the end of my T's to avoid that. I started doing that, I think, in college, actually. So what I start with is I start with the original denominator, 5t minus 3. And I take a derivative of the numerator. So what is the derivative of t squared plus 4? 2t minus the original numerator, which is t squared plus 4, times the derivative of the denominator. What's the derivative of the denominator? What's the derivative of 5t minus 3? 5. And it's all over the denominator squared. Okay, we have to clean this up. Please do not be tempted to do something like that. You guys see my red marks? Why can't I do that? Because this is a common thing that I see. It's not because there's a negative.
Well, I mean,
Oh, maybe you mean more of that.
yeah.
Do you mean because there's more after the negative? Two pieces in the numerator, right. So there are two pieces in the numerator separated by the subtraction sign and the negative. That's exactly right, Eric. Thank you. And this piece doesn't have a 5t minus 3 in it, right? That's the problem. So yeah, no canceling like that. I can clean it up though by multiplying things out. So this would be 10t squared minus 6t, and then minus 5t squared. Again, remember this negative applies to both pieces. Another common mistake, so minus 20, not plus 20. There is like almost never a reason to multiply the denominator out. Like it never happens. So don't do that. That's not useful. Leave it factored. The numerator will clean up. I have 5t squared minus 6t minus 20. Is that right? And then the denominator is 5t minus 3 squared. It is possible that the numerator could factor and reduce with the denominator. That could happen. Does anybody know why, just looking at it without factoring the numerator, it's never going to cancel with that particular denominator? Can anybody look at that and tell me why? Yes, you got it, Cooper. So, Connor, I'm sorry, Connor. Connor's right. So if you're looking at the 5s, there's a chance that I could actually factor the numerator to have a 5t, right? Like that would happen. If it factors, that would happen. But the problem is that I could never factor the numerator's 20 right here to give me a 3. Are you with me? So that's why on this one, there's really no need to factor the numerator because the 20 will never factor into something with a 3, and the only reason to factor would be to reduce, and it won't reduce. So our calculation is finished right there. What was it called? G of t? And this would be our derivative. Just right like that. Okay, the next one has a bit of trig in it. Oh, I wanted to show you one more thing, actually. Let me go back to this slide over here. There is a mnemonic device that I always say in my head when I do this, because I had a high school teacher that said it this way. Maybe you have an example of something like this too. My high school teacher wrote this as high over ho. Sometimes I've seen it as high over low. So if you actually think of it as the high function over the low or the ho function, this is ho-de high minus high-de ho all over ho-ho. So let me show you. This is the denominator. This is the derivative of the numerator, d high, over the numerator, high, the derivative of the denominator, d ho, and then Santa's on bottom. And that's always fun, ho ho. Do you guys know where high-de ho is from? It was a TV sitcom years ago. Home Improvement is it? Yes, it was on Home Improvement. So, okay. If it helps, use it. If it doesn't help, don't use it. I don't care. It doesn't matter to me. It's something that stuck with me because mnemonic devices do help me. Let's do another example. So on this one, we do have some trig involved. And because the trig is on top and we have a polynomial on bottom, another reason why we couldn't simplify this in any way, shape, or form to actually take a derivative of the simplification. So we do need the quotient rule for sure on this. The quotient rule says I take the denominator times the derivative of the numerator. So what is the derivative of sine?
Cosine.
Cosine, that's right. Symbol for subtraction, right? Make sure we've got a subtraction when we're doing quotient rule. And then we do it reversed. What's the numerator is next, right? Sine x. And then the derivative of the denominator. So what's the derivative of x cubed? 3x squared. All over the denominator squared. So x cubed squared. We can clean this one up, even with some reducing, actually. So I have x cubed cosine x minus 3x squared sine x. And then what is x cubed squared? X to the 6th. So this one still has subtraction in it, like we talked about on the last one. So it can't just cancel things out sort of randomly, but in fact, all of the pieces of the numerator do in fact match with something in the denominator. So I can simplify. How many of the x squareds are going to cancel out? 2. I meant to say how many of the x's are, and you answered 2. That was supposed to be what I was supposed to say, yeah. How many of the x's are going to cancel out? 2. So x squared will cancel out. So x cubed will become x cosine x. The 3x squared will become 3, and then sine x. And then the x to the 6th will become x to the 4th. Yeah. H prime of x. All right. So it's actually a fairly nice place to stop if we don't get finished. What's next and what we will finish up next time will be trigonometric derivatives, okay? So this section, 2.3, I will go inside of WebAssign and I'll adjust the due date for it, so don't be worrying about it. But I would encourage you to go ahead and do the WebAssign for this up to the point where it hits all these derivatives of these other trig functions that we haven't discussed. And we'll pick up there next time.